Um, Welcome from Switzerland and from a beautiful sunny day. My name is Arno and I'm the conductor of this 45 minutes webinar about power quality. What do we mean about power quality? First of all, electricity is perhaps the most essential source of energy used by commerce and industry today. Anyway, it comes to an unusual commodity because it can be seen, it can be conveniently stored in quantity, and it can be subject to quality checks before it is used. So on your screen you see a picture on the left side which represents a common network, from the network plants producing a perfect electrical signal down to the application. Unfortunately, during its way through the several network components, like impedance, breakers, transformers, and loads, its quality will be affected. The quality needed depends on the application. What is good for me, it might not be good for someone else. So, just how much deviation from perfection can be tolerated depends on the user's application. For instance, myself, I am driving a very common car in Switzerland. I need it for my business and private journey. Its quality is perfect, it's good enough. Obviously, if I'd like to participate to a Formula 1 race, its quality won't be enough. So, once again, the quality level of a product, in this case the electricity, is related to the requirements of the application. What can influence the power quality? Now, drawing a borderline at the PCC, at the point of common coupling, between distribution network and users, we can see, or we can distinguish between influences coming from the network or generated within the load, which could propagate in turn onto the network and so affect next to users. Atmospheric events such high winds, freezing rain, lightning may cause damage to overhead lines. Lines and transformer switching could also be sources of disturbances. From the load side, a problem on one customer network may affect next to users on the same subsystem. Anyway, again, the quality that we feel depends on the claim of our own application. Frequently occurring power quality problems. Computer lockups. A lockup occurs when the PC appears to freeze. Causes can be the system itself, for instance an obsolete operational system, or could be the voltage variations generated by parasite currents flowing along the line impedance between devices and grounding, affecting the low voltage signals, typical 5 volts by IT devices. The flickering or flicker effect is nothing else than the voltage variation which causes nuisance light flashing. An excessive flicker can even cause migraine. This flicker effect will be explained more in detail further on. Break in production. Continuous process operation where short interruption can disrupt the synchronization of the machinery. A typical example is the paper making industry, where the cleanup operation is long and expensive. A power factor correction. The impedance of capacitors banks reduces as frequencies rises is known. Capacitors are therefore likely to carry quite high harmonic currents and damage can result. For harmonic frequencies can coincide with the resonant frequencies of a circuit, creating excessive current leading to a failure. Or the neutral overheating. In the past, installers used half-sized neutral conductor. The triple harmonics adding the neutral. Some cases in commercial buildings show neutral currents between 150 and 200% of the phase current, resulting in an overheating of the neutral conductor. Nuisance stripping. Residual current breakers operate by summing current in the phase and neutral conductors. Now, the presence of leakage current harmonics flowing through the installation capacities can generate unwanted breakers tripping. The most obvious power failure are complete interruptions and voltage dips as well, where the voltage drops or rises for a short duration. These variations are measured as an RMS value. It means average value over a time which can range from milliseconds to some hours. Causes can be from outside coming, from the distribution system or other branches of the network, or from inside, for instance, heavy loads switching. When heavy loads, such as large motors, are switched on, the starting current can be many times the normal running current. Since the supply and the cabling of the installation are sized for nominal running current, the high initial current causes a voltage drop in both the supply network and the installation. The magnitude of the effect depends on the network impedance. Interesting is that dips caused by starting currents are characterized by being less deep and much longer than those caused by network faults. Now, a voltage dip can be graphically represented, as you see on your screen, in two ways. As a sine wave or an RMS value, what actually is more usual. Both provide the same information: start, stop, duration, magnitude. The advantage by the RMS value is the reduced size, which can save memory and accelerate data transfer in case of a remote communication. The flicker effect. The flicker effect is nothing else. We say that a voltage variation, but a specific one, having the characteristic to be visible and nuisance. Tests in laboratory have demonstrated that the human eye is very sensible at voltage RMS variation, in other words, 50 Hz modulation, which frequency is around 8 Hz. The flicker itself has no unit as volt and amps. It is defined by artificial units called PST and PLT, short time and long time. The PLT unit, which is valid for the standard and its unit values is 1, is calculated after 12 PST. Causes of flicker. At the medium voltage level, we have arc furnaces, welding machines, and induction furnaces are large metal melting systems employing irregular powerful arcs to generate heat. At low voltage level, instead, switchings of heavy loads related to the line impedance can generate flicker. At the generation side, the aeolic system are known as flicker producers also. The energy generations, we can say, depends on wind humor. Just consider that it seems that this kind of generation is increasing with a rate of about 30% per year. The blackouts. Blackouts are the most basic of power quality problems, lasting from several seconds up to hours. Of course, the public supply is not the only source of failures. Within the installation in a building or plant, there will be many areas where the failure of single component, cable or connection will cause complete shutdown. A voltage drop is considered as an interruption when the voltage decreases below 1% of the nominal value. Many operations are sensitive to even very short interruptions. For instance, continuous process operations, like paper-making industry, where a short interruption can disrupt the synchronization of the machinery. Or multi-stage batch operations, semiconductor industry, where the production of a wafer requires a few dozen processes over several days. You can imagine the failure of a single process is catastrophic. Or by data processing, for instance banks, where the cost of the processing itself is low, but the value of transactions can be very high. So to overcome energy failures, large consumers such as steel and paper-making industries will require a second supply. So that a single failure is very unlikely to affect both supplies. For smaller industries with lower power requirements, it may be considered to have an on-site generation, backups generators, UPS, to handle essential equipment during blackouts. Downtime are expensive. Downtime can have high cost. The cost of power quality problems is in terms of lost output and disruptions varies depending on the type of industry. Production interruptions might cause significant financial losses owing to the missed in production. Imagine deadlines for time-sensitive advertising for a newspaper publisher. Now, according to an European power quality survey, it is clear that the industrial sectors annually lose billions of euro as a direct result of their electrical power installation not being sufficiently reliable for today's and future operating demand. Always according to that survey, what was surprising as well was, and possible still is, the relative lack of analysis and measurements that take place among these power critical industries to be able to know what is causing these damaging interruptions to their operation. Transients. Transients are very short voltage changes, which duration is of few microseconds, usually measured against Earth. The magnitude can reach several thousand volts. They can cause serious damage to both the installation and the equipment connected to it. The two principal sources of transients are lightning and switching of electrical circuits. Consider that a lightning stroke can generate electrical values around 25 kiloamps to 30 megavolts, so a very high energy content. The first step in protecting sensitive electronic devices against transients is a good installation practice, including an efficient grounding system. There are components called TVSS, Transients Voltage Surge Suppressor, or VCD varistors, which can also be applied to protect sensitive devices. You can see some pictures representing transient effects. Owing to the high energy content, insulation materials can be seriously damaged. Unbalance. Unbalance is an important issue of power quality, mainly affecting low voltage distribution systems. The system voltage at the generation side is generally symmetrical. Small-scale generations, such as photovoltaic installation, are sometimes connected to the grid by means of single-phase inverter units, what can lead to an imbalance effect also. In most practical cases, is the asymmetry of loads the main cause of imbalance. At the high and medium voltage level, large single or dual loads, such as AC railways or induction furnaces, can be connected also and generate imbalance. At the low voltage level, usually are single-phase loads, for instance PC or lighting systems, the cause of imbalance. Also, the network faults as face-to-face, face-to-ground or face-to-face, and open conductor faults can affect a balanced network. Consequences: by a rotating electrical machine, three kinds of problems can be faced owing to the imbalance. First, the torque is limited by the negative sequence, generating a negative braking torque. A mechanical problem: the bearings may suffer mechanical damage, and stator and rotor are heated excessively, what leads to a faster aging. By transformer, the efficiency is affected. This picture shows a thermographic analysis of a motor checking surface temperature. The voltage imbalance can be one of the causes of motors overheating. By this analysis, we have to take care and consider that the internal temperature, winding temperature, can be about 10 degrees Celsius higher than what is measured on the surface. Harmonics. In an ideal, clean power system, current and voltage waveforms are pure sinusoids. What unfortunately is no longer the case in our networks. The electrical harmonics wave and the music harmonic sound wave have a similitude. Their frequencies are integral multiples of the fundamental frequency. In the electrical field, a harmonic content generates a distortion of the sine wave. The current shape is different than the voltage shape. We are faced to a load that draws current in a no-sinusoidal fashion. The picture on your left shows a flat topping voltage originated by a very distorted current over the supply impedance. Harmonic distortion caused by nonlinear loads results in current higher than expected owing to the content in harmonic frequency components. The harmonics content is represented by bars graph, as you can see on the right side, called frequency spectrum. Any cyclical waveform function can be divided into sinusoid and the fundamental frequency plus another. This mathematical procedure used to break down in harmonic content is called Fourier transformation. In case you will have the possibility to connect a power analyzer to the power supply of your AC PC, very probably you will be faced to the same results that you see on the screen. Harmonics are characterized by order, frequency, phase, and sequence. By the order, we have odd and even harmonics. Even harmonics are nowadays rare. They are generated by an unsymmetrical waveform where the positive and the negative half cycles have different shape and magnitude. They were common when half-wave rectification was widely used. For instance, long time ago, black and white television used a simple diode cutting up sine wave, producing the second harmonic. In a clean network, we have a positive sequence only. Harmonics and unbalance generate the negative sequence. Negative sequence harmonics, or the fifth harmonics, have the characteristic to generate a counter field which reduces the efficiency of rotating machine. In turn, the zero sequence harmonics, triple harmonics, or multiple of the third harmonics add themselves in neutral. Skin effect. An alternating current tends to flow on the outer surface of the conductor. This is known as a skin effect, and it is more pronounced at high frequencies. The skin effect basically decreases the effective cross-sectional area available for the flow of current, thereby increasing resistance with heating. We can say that above 350 Hz it might become significant. Now, to help overcome this problem, multiple cable cores or laminated bus bars can be applied, can be used. Influences of harmonics on electrical machine, motors. Voltage harmonics goes, as we said, extra losses in direct line connected induction motors. The fifth harmonics create a counter-rotating field, whereas the seventh harmonic creates a rotating field beyond the motor's synchronous speed. The resulting torque pulsing can cause problems on couplings and bearings. Since the speed is fixed, the energy contained in these harmonics dissipated as extra heat, resulting in premature aging. Harmonic currents are induced into the rotor, causing additional heating also, reducing, by the way, the efficiency even further. By transformers are affected in two ways by harmonics. Firstly, the eddy current losses, normally about 10% of the loss at full load, increase with the square of the harmonic order. This results in a much higher operating temperature and a shorter life. The second effect concerns the triple harmonics. When reflected back to a delta winding, they remain circulating in the primary. This results in a higher temperature and saturation. Equipment such a transformer is usually expected to last for 30-40 years. Now, having to replace it in 7-10 years, you can imagine the serious financial consequences. Influences on protection tripping. Breakers are overcurrent devices, but it is the heating of the breaker owing to the current that makes the breaker trip. Frequently, the overcurrent rating is too close to the nominal current, maybe because it is underestimated. And the circuit is prone to so-called nuisance tripping, caused by the harmonic content. By protective relay, the RCD, residual current devices, leakage currents may reach thresholds that cause them to trip. Resonance effect. Capacitors do not generate harmonics. They are linear loads, but create resonance circuits LC with the inductive elements of the installation. The definition of the maximum resonance is when capacitive reactance equals inductive reactance. An LC circuit consists of an inductor represented by the letter L and a capacitor represented by the letter C. When connected together, an electrical current can alternate between them at an angular frequency. In case a nonlinear load generates an harmonic signal, which frequency corresponds to the LC frequency, then this harmonic frequency will be amplified. This amplification of harmonics, owing to the resonance, is a source of a variety of problems, including excessive currents, blow capacitor fuses, or can damage capacitors, which can even explode. The power factor. Harmonic can affect the power factor also. By linear loads, only we used to speak of cosinus phi, which represents the phase angle between current and voltage. It is represented by a bidimensional diagram. The cosinus phi in that case equal the power factor. Now, in presence of nonlinear loads, the representation becomes a three-dimensional diagram because of the distortion factor. Now the ratio active power and apparent power has changed, therefore the cosinus phi is different than the power factor. I do apologize, I have some problem with this picture. Let's carry on. Harmonic sources of harmonic. In the early day of power supply design, the common single-phase power supply was linear. Nowadays, every electronic machine, PC, printers, copy machines, is using switched mode DC power supply. The advantages are reduced power losses and reduced size and weight of inductive component like transformer. You can imagine the advantages in, for instance, aeronautics applications. The drawback consists in the generation of harmonics. The PC-type loads are characterized by being rich in all the low-order harmonics with very high contents or level of the third, the fifth, the seventh, and the ninth harmonic. By electronic lighting balance have become popular for improved efficiency. Again, the drawback consists in generation of harmonic in the supply current. Speed controllers, UPS, and DC converters are known as harmonic producer also. Finally, it is estimated that more than 50% of the electrical energy demand comes from nonlinear loads. So you can imagine the influence of nonlinear loads on the quality of the product called electricity. When phase currents consist of the fundamental current only, the summation is zero. If the phase conductor contains both fundamental and triple harmonics, the result is different. Triple currents, as we said, will add in the neutral conductor. We are faced to overheated neutrals. This picture shows a network analyzer measuring a third harmonic in the neutral, where you see the value is over 97% of the RMS value, a very high content. This slide shows some situation that can be faced into a network. From the left side, we have a delta white transformer. What is typical in medium and low voltage level, which can trap triple harmonics. Now, assuming that there is a generation of the first harmonic at the low voltage level, as mentioned, triple harmonic enter the neutral, returning to the start point of the transformer. They will be stopped at the primary The advantage is they are stopped. The disadvantage is the primary will warm up and saturate. In the second example, we are simulated a fifth and the seventh harmonics, which will be stopped because of the delta and the Y configuration at the secondary provide harmonic in counter phase. It means the fifth harmonics at the secondary of the delta and the Y transformer will be in counter phase, therefore they will nullify one another. Filters can be applied in order to remove unwanted harmonics. A passband filter is a device that passes frequencies within a certain range and rejects or attenuates frequencies outside the range. Thus, knowing the harmonic generated by a nonlinear load, it is possible to calculate an adequate passband filter in order to short-circuit remove those frequencies. Or a low passband filter is a filter that passes low frequencies but attenuates signals with frequencies higher than the cutoff frequency. Thus we will permit, for instance, the 50 Hz to pass through and stop higher harmonic frequencies. Anyway, in some installation, the harmonic content is less predictable. A convenient solution are active filters or intelligent filters. Active filters, sometimes called AHC, active harmonic conditioners, continuously monitor the harmonic current demanded by the load and counteracts the harmonic by injecting equal and opposite signals into the supply to cancel the offending waveform or signals. Protective earth. A neutral to ground measurement is expected to be 0 volts or close to it. If the measured voltage is much higher, it indicates the presence of a ground loop caused by grounding at 2 or more locations. A good grounding is an important issue in order to avoid ground loops current. All sensitive electronic equipment must be properly grounded to assure both safety and proper operation. Large computer installations such as those of data processing or process control need special attention because they consist of many separate pieces of equipment that are interconnected. A different potential between two ground points can lead to a current which can flow through the available paths, such rake frame steel, bolted rake-to-rake joints, electronic ground, and device housing. And depending on the impedance, disturbances in form of voltage signals can occur, which can affect the current operating of electronic machines. So an equipotential grounding is necessary for the computer room. This picture shows a Fluke power analysis system measuring a leakage current with an RMS value above 1 amps. As already said, leakage currents may reach thresholds that cause RCD devices to trip. Damages owing to leakage ground currents. Display can be affected, hang-up of PCs, data transmission can be affected. Wrong triggering of protection influences on person and the corrosion of piping system, especially by, in this case, by DC current. We now approach to the end, and we will see the two main standards used in this field about power quality analysis. The first one is the 50160, which specify the limit values of voltage characteristic at the point of common coupling, PCC, and it is applied at the low and medium voltage level. The second one, more recent, is a 61430 and is applied to the instrumentation and defines the power quality measurements methods or procedure and the accuracy to ensure comparable results between different measuring instruments. This standard 61430 classifies devices in class A and class B. Class A devices are more accurate, and usually they have to be applied in case of dispute between who is selling and between who is buying the electricity. This table displays the parts that characterize the product electricity and the corresponding limit values according to the standard 50160. Anyway, for sake of honesty, we have to say that those limit values may change or may be applied in a different way from country to country. For instance, Denmark and France do not consider the 95% of the time, they only consider the 100%. Or a voltage change plus minus 10%. In Spain, plus minus 7% is applied. You see, those values, those limit values can change from country to country. In Norway, for instance, they have had a new parameter, the fast variation as well, what actually is not used in the other countries. So we are speaking about European standard. Anyway, as I said, for sake of honesty, we have to say that it may be applied in different ways. Countermeasures. First of all, it is important to say that there is no single solution to power quality problems. For each type of problem, there is a range of possible mitigation. In the real world, it is like that several problems will coexist, and the solution adopted must be compatible with each other. It is also important to realize that the network is dynamic. A large office building, for instance, may have hundreds of changes per year, so the harmonic spectrum changes continuously. So there is a difference between analyzing a product, electricity, or the product called electricity, and product that use the product electricity, for instance, frequency converter, machines, motors. When I do analyze a motor, I will need a couple of minutes. I will switch it on and switch it off, and I will get my results. Instead, when I do analyze the product electricity, because of the network is something dynamic, what I am measuring on Monday may be very different than what I'm measuring on Thursday. What I will get on January will be different than what I will get on July. It means that I will have to do measuring campaign. I will have to proceed to make long-term analysis in order to capture, let's say, the worst case, which will permit me to take the right decision. Again, because of the product electricity is something dynamic, is changing, is not visible, is very particular. So the only possibility to know what has to be done is first to know. It means we have to measure. Operation of short duty cycle equipment such lift and metalworking machine cause local voltage variations that have to be added to those originated by the distribution system. Anyway, again, in order to take the right decision, we have to know, and measuring is knowing. Now we said measure, it is the first step in order to take the right decision. Taking the right decision provides quantitative and qualitative benefits. It permits to save money and time and to improve the experience, to improve my experience as a network responsible, and my competence will be appreciated from colleagues and the management. You see, Fluke offers a wide selection of power network analyzers with professionals and user-friendly software that help to maintain a good power quality of your electrician domain. Fluke also offers a complete range of thermal cameras for both industrial and building application. Models are available for any budget. And the Fluke web page at the end provides additional product information and the schedule of further webinars.
Yeah, sorry, Arno, we have some time, so we can accept some questions. Thank you for your presentation first, because you took some time, and I know you really wanted to be